next talk will be by David Ellis, and he will talk about understanding Axion Minicluster formation and observational structures and observational signatures.
Thank you for allowing me to come here and speak today. Thank you also to Jens and Javi for your talks earlier, particularly because a lot of the content overlaps, and so it'll help me save a little bit of time going through this. So my name is David Ellis. I'm working with Dottie Marsh at the University of Gottingen, specifically on the formation of Axion Miniclusters and trying to figure out how we can see them. So quick overview, I'm going to talk very briefly on Axion theory. We've already heard a lot about it today. Then talk about how we can use a process called peak patch, which Jens discussed a little bit, to calculate the Axion Miniclusters, the Halo mass functions of Axion Miniclusters. Then we want to extend this to look at how we can use this to estimate the concentrations of miniclusters, which is much more interesting, particularly in the context of how we can then go about looking for them using microlensing. And then finally, I'll talk a little bit about minicluster substructure and what that might mean for microlensing also. Okay, so as I said, there's two Axion scenarios. The first involves the PQ symmetry breaking before or during inflation. And in this scenario, the Axion field takes a different value at each point in space, but these areas of space then get blown up to larger than the observable universe. And so we just have to deal with a single value of the Axion field that could be anything between -pi and pi. And so when you want to then calculate the radical density, all you have to do is solve a single ODE. And this is very easy to do. So this example plot I have here, I did on my personal computer in a matter of seconds, give it to master students as a homework problem. The second scenario, it's not quite so simple. So here the Axion field takes, as we heard from Javi, takes on random values on the scale of the Hubble patch, and then this causes us to have topological defects such as strings and domain walls. And as I'm sure Javi can tell us, or has already told us, this isn't so simple to simulate. And then as these objects decay, we get large amplitude, small scale density perturbations. And so here we see sort of a typical distribution of these from paper from Kopf-Katchow. And we see that we have some very high density tail of rare, very overdense regions. And what this means is that very early in the universe, we will have locally matter overdense regions, which will then collapse into objects. So we want to use peak patch to simulate this. What is peak patch? This is the algorithm that was first developed by Dick Bond and Stephen Myers, and then later developed further with the help of George Stein. It's the technical definition is it's an extended Pressure model which solves the excursion set in real space. So what does that really mean? The excursion set is just areas in which the density field is greater than some threshold. Okay, and where Pressure works on the power spectrum, assuming Gaussianity, peak patch works on the true density field. So here is the initial condition field, the initial data field that we use, and I think this is the third talk that has been mentioned now. It was generated by Javier Redondo and collaborators, and this is the same initial condition set of initial conditions that were used by Jens and Benedict in their n-body simulations, which Jens talked about earlier. So we have these n-body results to compare to throughout. Okay. Additionally, where Pressure is purely statistical, the peak patch tracks individual overdensities. And so we can say something about the mass and final positions of individual halos, much like you can do with n-body. Additionally, where Pressure assumes Gaussianity, it therefore loses a lot of these very rare high initial overdensities. Peak patch captures this full non-Gaussianity. Okay, and so we have our own version of the peak patch code developed by Christoph Behrens, used to be a postdoc here at Gottingen. And here is a comparison to n-body. I should also say that peak patch is obviously much quicker it takes orders of magnitude less computing time to run a typical peak patch run. And so here we have a comparison with n-body. We see, so Lagrangian coordinates basically just mean that we've taken out the displacements. So this is on the initial density field, and Eulerian includes them. So the blue circles are the n-body results, so the halos as found by the Rockstar halo finder, and the red circles are then the sort of best match that we think the peak patch. We think that we're looking at the same objects now in peak patch, and we see that we have a fairly good. These match fairly well. This is only using first order displacement calculations. The code now does actually include second order as well, but we don't actually use these displacement calculations in this particular piece of work. What we can see though on the left hand side is that in the Lagrangian space, in terms of the initial on the density field itself, peak patch works a lot better. We can see that there's an almost one-to-one agreement with where these particles, so these particles that we have in these blue regions, when we backtrack them to their initial positions, peak patch knows almost exactly where most of these are. Okay, so how does peak patch actually work? So we need to linearly evolve our density field. So this just amounts to essentially time multiplying by the growth factor. And then we have to smooth on a variety of scales. And if any cells are overdense on any of these scales, then it's considered to be part of the overdensity. So I have a animation here. So we see that at the lower redshift, we only have one halo in this 1D example. At a later redshift, we have two, and then finally we can see that these two objects have merged into one large halo. Okay, so that's the general principle, but I should say that for ordinary standard standard WIMP CDM, the overdensity is fixed at, the threshold overdensity is fixed at a value of 1.686, very familiar value, but we need to make two modifications to peak patch to be able to use it to simulate axionic dark matter. The first is that we need that our threshold is no longer this fixed value, specifically because the Axion Miniclusters can collapse early into the radiation domination era. We have to take that into consideration as well. And for the same reason, our growth factor is also different. So what do? So our growth factor is now given by this function here because the Axion overdensities are adiabatic perturbations. The growth factor comes out looking like this. And what this basically means is that the growth factor tends towards 1 for very high redshift. So Z is just the scale factor divided by the scale factor at equality. So you can see that when the redshift's greater than that of equality, the growth factor is around 1. And for after equality, it grows much like it does with a CDM. But we need to relate this to the nonlinear evolution. And so we have to solve the spherical collapse of one of these overdensities, as done by Carpenter-Kirchhoff previously. And again, as I said, we have to include now the radiation density. So here's an example. As we would expect, we have higher initial overdensities collapse earlier. And what we can do is we can look at the point at which, if we involve this also linearly, we can ask, well, at what point does this overdensity collapse when it's linearly evolved? So we can go through this process for each overdensity, and we can work out a threshold of collapse that looks something like this. So for very high redshifts, we require the overdensity to be very large for it to be collapsed, and as we would expect, it tends towards the traditional value at late redshifts. Okay, and so we can now plug all of this into peak patch and calculate the halo mass functions. So the solid lines now are our results from peak patch. The dotted lines are the n-body halo mass functions that Jens presented earlier, and I believe Javi did as well. And we see that they're in fairly good agreement. We have the same power law function. We see we also get something of this peak that Jens was mentioning, although it's maybe slightly different at very high redshifts. And one thing I should mention is that we, just the same as Benedict Eggemeyer and collaborators in their n-body simulations, we consider a maximum mass of 50 micro eV. But what's important is that all of the mass scales can be, all of the masses can simply be scaled by the axion mass quite easily. And so if we want these to be, if we want to consider higher masses, we can just shift these basically in the mass direction by considering a smaller or larger axion mass. Okay, so that's all well and good, but we could basically have done this using Pressschecter. What's more interesting now is trying to use peak patch to estimate the concentrations of these objects. Okay, so it's been known for a while that the concentration of a halo is somehow dependent on the redshift at which it's collapsed. What does it really mean to be collapsed? Well, Navarro et al. Described this, they define this to be the point at which a halo, half of a halo's final mass is contained within progenitors, which have masses larger than some fraction of that final mass. So for them and also for us, we just chose a fraction of 0.01. So we add up all of the progenitors that are equal to, that are larger than 1% of the final mass, and we look for the redshift at which that equals a half of that final mass. And this is what makes up, this is what defines the collapse redshift. They then said that the scale over density of a NFW profile is proportional to the density of the universe at this collapse redshift, up to some constant of proportionality. Okay, and so one of the advantages of peak patch is that because the data sizes for each snapshot is much smaller than n-body, as well as the fact that we can run it a lot easier with a lot less computing time, is that we can get many snapshots for a single run. And so this makes it much easier for us to calculate the redshift of collapse. So here we have a very small example error region laid on top of the initial density, so the colors you see at the initial density field. And the black circles here are from peak patch. So we see that we have some initial objects forming, and these later come together to form larger objects. And so we can start at one of our final large halos and iteratively work backwards, looking at earlier redshifts, looking inside the region of that halo, to then build up merger trees like this one shown here. I think this answers one of the questions potentially, to some extent, that was given to Javi earlier about whether objects are formed via the merging of lots of smaller overdensities or whether they form by themselves. And I think to a large extent, these final Axion Miniclusters are formed by hierarchical structure formation. This is exactly why they form NFW profiles. And by doing so, we can then calculate the collapse redshift. But unfortunately, this is only one piece of the puzzle, because there was also that constant of proportionality that we had to calculate as well. And so we calculate that by comparing to results from n-body. And to make this slightly easier for us to fit, because peak patch will give us a distribution, we calculate the concentration mass curve, essentially the average concentration mass curve, through a sort of Pressschecter type calculation on the initial density, on the initial power spectrum. And this makes it easier to fit to the data, as we can see here. I should say that each one of these points isn't a single halo. This is averaging over a number of halos, and these come from, again, the results from Benedict Eggemeyer, Javi, Jens, and others. Okay, but now we can calculate from this this proportionality constant, and we can then apply that to, we can give the exact same value to Pressschecter and have a look at that distribution. So now that looks something like this. So we see that we have roughly the same sort of shape of our concentration mass relation. Again, we see we have these n-body results plotted here as well. So we have some mass at which the concentration is at a maximum. It goes down from each side from there. And this is really the advantage of peak patch, is now that because it's working on the actual density field, we can see this distribution of concentrations. Another nice thing is that for large concentrations, so long as your redshift of collapse doesn't change too much, and we don't think it should really after redshift of equality, the collapse, the concentration essentially just grows with the scale factor. And so we can evolve this line that we've predicted for redshift of 99, which is the final redshift of the n-body results, and we can project that toward to today. And we see that these concentrations are very, very large and peaking at around 10 to the 5. And this has quite significant consequences for the survival of mini-clusters, and therefore for the both astrophysical searches for trying to find mini-clusters colliding with neutron stars, but also with the possibility of searches such as ADMX, direct detection searches such as ADMX, looking for a more diffuse component. But because they're so dense, it means that they're less likely to be disrupted by stars and things, and therefore there's less. It's much more difficult, much less likely for these regions to pass over the Earth and therefore be detected by ADMX. Okay, so now we know that we're going to have these mini clusters that we think are very, very dense. So the next question is, can we see them through gravitational microlensing? So we've heard quite a bit about microlensing today and also yesterday. So quick recap. What is it? It's basically like regular, the normal microlensing or normal gravitational lensing that we think about, except that we typically only have a singular light source. We're looking at amplification of light from a single star, and we can't resolve the individual images that are produced. So this is a typical, a normal gravitational lensing scenario that we think of, where we have an entire galaxy that's being distorted, and we can see this full circle of images. But with microlensing, this isn't the case. So what happens instead? Well, for a point mass, the microlensing is defined to have occurred when the Einstein radius of the mass overlaps with the line of sight of the light source. So at this point, the amplification becomes greater than 1.34. So in the experiment, we just measure the brightness of this star, and then we look for events such as this one here. Okay, but there are some additional considerations to make now, because firstly, Axion Miniclusters are not point sources, although they are very dense. They do have some comparatively fluffy structure. Then we also need to consider wave effects. So this is also something you have to consider for primordial black holes. As we heard yesterday, primordial black holes are unconstrained by microlensing for masses smaller than around 10 to the minus 12. And this is due to wave effects. We also, in theory, need to consider finite source size effects. So the fact that the stars behind the stars whose amplification we're looking at aren't actually points objects. We need to consider effects of that as well. But this isn't considered in this particular piece of work. Okay, so for extended lenses, the threshold impact parameter is much lower, and this reduces the overall number of lensing events. So here we see a similar animation to the one before, but now we have a fluffy object that has a much smaller effective lensing radius. And as we can see here, so we have the comparison of the amplification as it would have been with a point mass or a mini cluster. And so we see a much smaller amount of time with the lensing above the amplification threshold. And so what this means is that in our typical lensing, rate of a lensing equation, so it's dependent on the fraction of dark matter that you think your objects make up. We have some integral over the line of sight from 0, which is the observer, to 1, the source. Most importantly, we have this integral over the impact parameters. And so there is some function of the impact parameters, and also it's obviously dependent on the number density of your object along your line of sight. But the important thing is that for extended sources, this threshold radius becomes lower, and therefore you're integrating up to a smaller threshold here. And so you expect to therefore see a smaller number of events. So what we can do is we can effectively map on what we expect from mini clusters in terms of lensing onto primordial black hole constraints by calculating the ratio of this effective radius to the Einstein radius of that object. And we can do that for each concentration and mass, and we can get a sort of lensing potential graph that looks something like this. And so up in this blue region, this ratio is very close to 1. So these are very centrally dense objects. They essentially lens like point masses. But as your Einstein radius gets larger than the scale radius, you very quickly get to a point where you're not able to see any lensing at all. The effective radius becomes 0. Okay, and so now you might be asking, well, where does the concentrations that we have that we calculated from our last paper fit into this? Well, it's probably not a good sign that I've left so much white space down at the bottom here. Our concentrations lie somewhere down here. Okay, but we don't need to panic just yet, because this is just our sort of average line. What we can also do is estimate the maximum possible concentration that each mass could have. And we do that by taking a look at the data, looking at the first redshift at which an object of each mass forms. And if we take that to be the collapse redshift of the object, we can therefore estimate the maximum possible concentration estimate the maximum possible concentration that an NFW profile could have for this initial density field. And this looks something like this. Okay, so we're still not intersecting with this blue region. It's worth remembering at this point, like I said, that if we consider lighter axion masses, then everything here shifts to the right. So potentially then you could intersect with some of this lighter blue region, but because of the way this slopes, you're still quite a way off with that. And then additionally, there's that last consideration that I said we have to include, and that is wave effects. And exactly because of this procedure that we've had to think about, in which we look at we have to consider a smaller lensing area, we're then also considering a smaller amount of internal mass. And as a result, for primordial black holes, this constraint stops you from being able to, the wave effects stop you from being able to lens for masses smaller than 3 × 10⁻12. For extended source objects, this is actually stops you at much larger masses, exactly because your effective mass is smaller, because a smaller amount of your object is doing the lensing. And so we can plot a line at which the effective mass is equal to this minimum, and that is up here in this corner. And so in theory, our objects need to be above this line now to be able to produce lensing. Okay, and so now we can see there's quite a bit of distance between this area and our potential and our theoretical maximum for these concentrations. So the question now is microlensing for mini clusters dead? Was that the last hope? Fortunately, it's not necessarily. There is another. And that's the fact that this is the third time we've seen this particular image today from Benedict Eggemeyer and others. We know that Axion Miniclusters have a very dense, very rich substructure. So in this graph, in this right-hand plot here, we can see that this one rather large Axion Minicluster is populated with very many smaller objects, which are formed from these rare high-density minicluster seeds that we saw earlier. And so the question is, do these objects look different? Because so far we've assumed that everything forms via hierarchical structure formation to produce NFW profiles, which generally only occurs after matter radiation equality. But with these high density peaks, they have the potential to collapse earlier than that, and may not form through the mergers of multiple objects. and therefore they may look distinctly different. One particular example is that we've seen in the literature has been suggested that if an object forms completely in isolation via self-similar infall, it will form instead a parallel profile with a profile of that goes like r to the minus 9/4. And this is what Malcolm Fairbairn, along with Dottie Marsh and others, considered previously, and what they considered was exactly parallel profiles that those have an average density given by this, what is for many of us a rather familiar formula from Kolmogorov, estimating the final average density based on the initial overdensity of some region. Okay, and so by fixing this average density and knowing the mass and the slope, they can then calculate the radius for each one of these objects. And this is exactly what we do in this work. And so we can, much like with the NFW profiles, we can now calculate the potential for lensing. And so we get something that looks like this over typical initial density values. And so this looks a little bit more hopeful. There's a lot more blue at the very least. And this area that's allowed that produces lensing from wave effects is much larger. So now we need to think about how exactly can we go about finding these very dense substructure. So what's important is that we want to be able to trace a link from the initial density field to the production of this substructure. So we turn once again to peak patch. We calculate and we run peak patch up to a redshift of 3,900. This is around equality. This is the closest snapshot we have in the n-body data from Benedict. And so we do this because we're looking for objects that exist at these very high redshifts. So they've obviously already collapsed, and then we can try and find them again as substructure in the later redshifts. And so what we can do now, and this is our current and future work, is that we can make a sample of, in this case, 7 test halos, and we can try and then look at their profiles and see whether there's some relations between this initial overdensity and their mass. And by doing so, we can calculate for, or hopefully we can calculate this entire spectrum, this entire distribution, what the potential lensing would be for these objects. Okay, so now you may be thinking, well, where do these 7 test points lie on our previous lensing curve? I should say that these we've chosen these 7 because they're very overdense and very high in mass, so we think they're the most likely to produce lensing signals, and they lie around here, which may seem like it's end game for lensing, but there's a few things to consider here. The first thing is that these objects exist at 10,000 redshifts around equality, whereas this lensing plot is calculated assuming that the objects are present at a redshift of 0 today, and therefore they still need to grow. And when they do so, it will reduce their initial overdensity because the area of the integral on the initial density field increases, therefore reduces the overdensity, but it also increases the mass, so it shifts the objects to the right as well as down. The other thing is that, as I said, as I've mentioned a number of times, all of these results can be shifted based on the axion mass. So for each one of these triangles for this particular region, we can look at an axion mass that's 10 times smaller, and yeah, so we can get even closer to this potential lensing region. And so if we consider axion mass is around 100 times smaller, which admittedly isn't the predicted masses is getting quite far away from these predicted masses that Javi told us about earlier, but then we're already within this region before they've even continued to grow. And so that makes up the body of our future work. Unfortunately, I can't tell you just yet whether these objects are going to be able to produce lensing, but basically because peak patch works so well on the initial density field, what we can do is we can use it to find particles in the initial distribution that we think will later be in some of these very dense objects. We can track these objects forwards in the n-body data. Again, this same data from the paper by Jens, Javi, and Benedict, and we can find their new local maximum using kernel density estimate, calculate their profiles, and then hopefully finally answer that question of whether these objects produce lensing. So just a quick summary, Axion Miniclusters do form very dense NFW profiles, but unfortunately these objects are not dense enough to produce microlensing signals. But we might find that substructure saves us. The substructure that's specifically formed for these very high rare density peaks, since we expect they could look quite distinctly different. And this is exactly what we're trying to do now, trying to piece together how these profiles will look. And so that brings me to the end of my talk. And thank you everyone for listening.
Thank you very much, David, for this nice talk. We have already the first question by Sasha Sakharov.
Okay, thank you very much. It was very interesting talk, but again, I would like to mention one thing. You know, you said that regime of gravitational lensing depend on, let us say, opportunity to resolve resolutions between images. It's not quite correct because our observational facilities are improving. So, for instance, even 20 years ago, Bogdan Paczynski said that in principle it's possible to resolve images for gravitational microlensing in our galaxy because the distance between images around milliarc second. In principle, it's resolvable. As I told you earlier, that Wamsgan suggested, let us say, definition for different regimes of gravitational lensing depending only on mass. So if mass is stellar mass, microlensing, it's called like microlensing because for cosmological distances between images have to be micro arc seconds. That is regime. So, and second, about extended lens model. So we also considered this kind of problems because many years ago, around 30 years ago, Alexander Gurevich suggested, let us say, extended object, he called it like neutralino masses, extended object with some distribution of mass inside of this object. Of course, light curves in this case would be slightly different, but also we analyzed this case, and since lens has to be transparent, in this case, important thing that caustic played a key role in this game, similarly to macro gravitational lensing. You know, because, you know, if you studied gravitational lens textbooks, so you, for galaxy, people use some, let us say, isotomal sphere models with core, etc., etc. But the most important issue is caustic in this game. It's a second remark. And last remark about wave optic approximation. Of course, there is a so-called Deguchi-Watson limit between geometrical optic and wave optic approximation. It's a well-known paper. But if you are saying that you used, for instance, if you fix mass of gravitational lens is 10 to the minus 12 or 10 to the minus 15. So in this case, probably you have to use even wave optic approximation, but also you have to clarify, let us say, a wavelength or frequency band for observations. Because in this case, exposure time is also very important. You know, because if it's, let us say, you exposure, because wave optic light curve should be very different from Paczynski light curve, as you know. But in this case, you have to simulate in your computer simulation, I mean, wave optic approximation. That's it. Thank you.
Thank you. To respond to the first one about the regimes, yeah, I understand that potentially we can see the different, we can maybe resolve the images from some particular microlensing, I've gone too far, from some particular microlensing events. But I think in terms of naming the regime, the reason why it's most useful to describe it as microlensing, as opposed to trying to call it something else, is because the calculation is still such that we're just interested in the single amplification of this object. So even though in this particular scenario the angular resolutions involved are probably much smaller than micro, I haven't actually performed that calculation. I think the ethos is the same as microlensing.
No. I completely disagree with your point. So there is a different thing, physical phenomena, and also way to discover this physical phenomena. And ways to discover physical phenomena is evolving and improving permanently. But terminology of process should not depend on our technology to find it. That is the message. Moreover, you know, many years ago, even because it's not known very well in Western literature, but even before Paczynski, it was, let us say, a Soviet astronomer Belka. He suggested this way to monitor background stars. But Belka was not astronomer. And he said that principle people could found some perturbation like 1% of luminosity for background stars. But Paczynski was an advanced astronomer, and he understood that it's possible to analyze light curve for million stars. In this case, this phenomenon could be discovered. But again, there are two different things. I mean, phenomenon and opportunity to find them. They're completely so. But of course, terminology have to be fixed. So because it's not my idea, I simply express some general opinion. So that is the point. Again, you said I'm seeing about finite source size effect, because finite source size effect is widely let us say analyzed and implemented in searches in microlensing. We published a couple of papers with including finite source effect. For instance, for pixel lensing observations, finite source effect is crucial because only giant stars may be detected. Microlensing only for giant stars may be detected with pixel lensing observation. Thank you.
Thank you. To address another one of your comments about the wave effects calculations, I understand that what we've done is relatively crude to map these things together.
No. Okay, so, but of course, people said it's probably, I don't know, probably Deguchi Watson was first people who said that if let us say observation wavelength is less than Schwarzschild radius for gravitational microlensing, you have to introduce wave optic effect because geometrical optic approximation is broken in this case. But your light curve was calculated for Paczynski light curve in the geometrical optic approximation. But again, if you're observing wave optics, so you have to also clarify exposure time for observations, and you have to clarify wavelengths or frequency band for observations.
Yeah. So in terms of I understand that it's specifically based on the wavelength of light you're interested in. I think we considered for this particular calculation as it's just as a test value. I think it was 6,000 angstroms, which is I think the same as the super searches for primordial black holes. And essentially, we just look for the point at which the effective mass is. Now, the Schwarzschild radius is smaller than this light, this value of the light.
Yes, so, in this case, surely you have to use wave optic approximation.
Sure,
but according to
the point is that we're staying to above.
Sorry, but too much probably.
To move also to another question, so maybe you can sort this out in a private chat, so to say. Yes. So Valerie, you had a question.
I have it's my misunderstanding. Can you repeat or can you repeat your idea of why the substructure is going to be helpful for microlensing or lensing?
Yeah, perhaps I didn't make that so clear. The reason, and I think this one's probably the easiest plot to show it on. The reason why we go into this white region here where we don't get any lensing is because so you zoom in from very large radii in until the magnification is such that it's above the threshold. But in this white region, we're now looking at the part of the profile where the density goes like 1 over r instead of the 1 over r to the 3. And at this point, we're no longer able to generate these large these amplifications. The reason why the substructure might be different is because if it does look like a r to the minus 9 over 4 profile, we don't encounter that problem. So then this is why, if I skip to this plot here, this is why this is all blue. It gets to lighter blue, but there's always a smaller radius you can go to, and you'll be able to observe some amplification. Your resolution will, obviously there's you run into issues of your temporal resolution of your measurements, but yeah, in theory, these microlensing events can still occur. Does that answer your question?
To some extent, but do you mean that the density profile is going to change the luminosity curve, or what? So what's going to happen?
So yeah, because the internal density is much steeper, exactly, we think that you'll be able to generate so for a graph that looks like I think I've gone past it. For a graph that looks like this, we will see amplification that goes above this threshold value for sufficiently small impact parameters. So that's the point, that we think that for these for power law profiles that are steeper than r to the minus 1, there will exist impact parameters at which you do get amplification that's large enough to be visible.
So you expect higher peaks for shorter time. Is that the?
Yeah, and then also less often because the size of your object that is able to lens is also much smaller. I guess the size of the peak would be basically equivalent to some smaller point mass. Right?
Okay.
Igor, you had another?
I think there is a confusion here. At least I am confused. David, when you consider mini clusters of that small mass, you still consider them, I have an impression that you still consider them as clusters of mini clusters, right? Mm-hmm. And then you assume this Navarro-Frank-White profile, but genuine mini clusters, seeds from QCD, also have that same mass, right? And they have different profiles and different densities, correct?
Yeah, and I think these genuine miniclusters that you refer to are exactly what we're looking for, that we think are probably largely bound in other, potentially they're bound in other objects. It doesn't really matter for us, our searching for them, because we're just looking at these high density regions.
As a substructure, but that creates confusion.
Sure. Yeah, I guess they can be substructure. They can also live by themselves.
Yeah, but it doesn't matter if they are substructure or not.
Sure. Yeah.
I would say that there are more original, genuine mini clusters at that mass range than clusters of mini clusters at that mass range.
I would potentially disagree because I know how big the largest mini clusters are. They just take, for our box, they take up a very large fraction of it, and therefore I think they essentially encompass a lot of the total mass, and therefore that's why I think a lot of the other objects are contained within that. But I think that there will also be a lot of, shall we say, loners as well.
Okay. So I don't see any question anymore. So let's thank the speaker again, and let's thank all the speakers of this morning and also the audience for the lively discussions. So we can now go something to eat and so on, and then we resume at 3 o'clock Moscow time.